Hi everybody, and welcome to Investigation 11A and 11B. Normally I do a video for each individual investigation, but these two investigations are fairly intertwined. They cover very similar topics, and I'll explain why in a few moments. And frankly, neither one of them really needs a whole lot of fleshing into, but I do still want to obviously give you this resource with the hopes that this will be helpful. So with that said, what we're going to be talking about in this video are thunderstorms and tornadoes. So we're actually going to be focusing on two of the US's biggest weather hazards. First, let's talk about thunderstorms. So first off, thunderstorms are basically just a storm with lightning and thunder in them. And there's actually not a lot that actually is required for a thunderstorm to get put together. And in Investigation 11A, you're actually going to be piecing together a certain situation and then determining, was this situation favorable for thunderstorm development? So here's what you need to know. First off, thunderstorms really only need three things to get going. The first thing they need is lots of moisture. And a big reason why is because moisture acts as fuel. This is the storm's food. Then you need some kind of trigger mechanism, something that takes all of that moisture and pushes it up into the atmosphere so that it can condense into giant cumulonimbus clouds. And then the last thing you need is some kind of supportive upper level winds. And this is important because this allows that trigger to be enhanced. And usually what we look for as meteorologists is what's called a jet streak. Basically a portion of the jet stream that has even faster than typical winds blowing in it. And the way that it works, if I were to, I'll just do this right here using my pen, if I were to actually draw the jet stream, it might look something like this. And let me actually draw a few lines, because when you're looking at an upper level map, that's what you see. So these lines right here represent upper level heights and so on. Well, what actually happens is whenever you have a situation like this, what we have right here is what's called a trough. And then the thing in between here, the center of the trough, is what's called the axis of the trough. Now what actually happens is right at the axis is where we get that jet streak. And I'll circle that here in red. So usually what happens is over here on the eastern side of the jet streak is where you get favorable upper level conditions. And really the main thing you're looking for is what's called divergence. Basically you'll notice, and I drew it a little bit more over here, but basically these lines begin pulling apart. And that actually causes what's called divergence. And then in order for divergence to happen, or a result of divergence, is that air from below rises up to take the place of the air that's spreading apart. And so that's a major lifting mechanism that's necessary for thunderstorm development. Now with that said, I actually pulled out a couple of maps that are a little bit more current rather than the ones that you're going to be using in this exercise, partially because I didn't want to give away the answers. But let's talk about what's happening here. So here we're at the surface, and over here in particular, there's actually a lot of green, yellow, and then if you actually look closer towards areas like Boston over here or down here towards New York City, there's actually a lot of red. And typically when we look for thunderstorms, that's what we look for. We look for those centers of heaviest rain. And if you actually notice, just to the west of this, we have a cold front. Well, a cold front is a triggering mechanism. It is actually something that can cause uplift to occur and then cause thunderstorms to develop. Now, as far as moisture is concerned, we can actually determine if the air is moist or not by looking at the dew point temperatures. And I don't want to give away answers, but here is what I'll say. So let's look over here. Let me pull out my laser pointer. Let's look at these regions ahead of the front. And if you notice, a lot of the dew points ahead of the front are relatively high. So remember, dew point is the lower left number on a station model. Down here in Key West, it's 70. Up here in Tampa, it's 69. Over here in South Carolina, 67, 64. So we have dew points primarily in the 60s, 70s, a little bit of 50s up here. But watch what happens as soon as you go behind the cold fronts. Now you're on the other side of the front. Dew points are in the 40s, 30s, and even 20s. So what this actually points out is that there's a lot of favorable a lot of favorable moisture, a lot of favorable necessary moisture here at the surface. Now, speaking of upper levels, the other thing that is present right around the same area is a jet streak. And let me tell you how I know that a jet streak is here. So this map right here, this is the 300 millibar contours isotax map. You'll see one of these in the next activity or the next investigation. But if you actually notice, pretty much all along here, so pretty much all along the mid-Atlantic region, over here into the Ohio Valley, and then over here into the Mississippi River Valley, there are very, very fast blowing winds. That is indicative of a jet streak. And then over here on the eastern end of this jet streak, all of these contour lines are starting to pull apart. That is divergence, and that is a triggering mechanism for thunderstorms. That is a favorable thing for thunderstorms to develop. And if we were to go back to our previous map, what do you know? Right there, right off the northeast coast, we have thunderstorms. And right over here, we have the favorable environment for thunderstorms to develop. One of the big hazards, so now we're actually going to switch over to 11B. One of the big hazards that's present in thunderstorms is tornadoes. And tornadoes are oftentimes, in fact, I'd even say that they are the most intense hazards from thunderstorms. They could be over a mile wide, have wind speeds in excess of 200 miles an hour. They can cause some tremendous damage. Now, most tornadoes are common or occur in the months of April through June. And this is what we call tornado season. And the reason why these particular months are the most favorable is we have winter battling out with summer. We still have plenty of cold air up in the northern part of the country over the Rocky Mountains and up into interior Canada. But in the southern part of the United States, we start getting a bigger influx of warm, moist air. And as I just mentioned a few minutes ago, warm, moist air, good for thunderstorms. And so the conditions are just perfect during April through June. I will say one thing. On this particular module activity, or on this particular investigation, there are actually a few difficult questions when it comes to looking at this one graph. And they want you to look at the gray bars on the graph. But I'll just tell you right now, tornado season is April through June. So at least I hope that'll help as you're looking at that graph, that primarily tornado season is April through June. Now, with that said, what makes the difference between a typical thunderstorm type of setup and a tornado setup? Well, in order for you to have tornadoes, you still need to have the same conditions that you had with thunderstorms. But you need a few more things. And those few more things in particular are what is called vertical wind shear. And so think about this. If you were to launch a balloon on the ground, if you were to launch a balloon on the surface of the Earth and it were to float up, as it's floating up, the wind that is pushing it may actually change directions or even change speeds as the balloon is rising. That's what vertical wind shear is. Now, here in the Northern Hemisphere, typically the way that wind shear works is you start at the surface with winds coming from the south. And that usually gives you that warm, moist air. However, as you begin to rise into the atmosphere, you get up to the 700 millibar level, the 500 millibar level, and then the 300 millibar level, the winds start to shift. They start going from south to southwest to west-southwest and then to west. And so you have this changing direction with height. But a lot of times you also get changing speed with height. The upper portions of the atmosphere have less friction, and as a result, you get faster winds. When you combine these two things, this creates rotation. So now not only do you have these thunderstorms forming, but you also have rotation occurring in them, and that rotation is then what allows tornadoes to develop. Just a little bit more about wind shear. There are two types of wind shear. The first type of wind shear is what's called directional shear, where as you rise up in the atmosphere, the wind direction changes. The second type of shear is called speed shear. Here, the wind blows in the same direction the whole way up, but it gets faster as you go up. Now, either one of these two situations can still create rotation, but it's usually when we have a combination of them that we end up getting the most intense tornadoes. And so what you're actually going to be doing in this exercise is you're going to be looking at surface conditions and comparing them to upper level conditions to determine, is there wind shear and what kind of wind shear it is. To be honest with you, most of this is stuff that you've already done. So we're just giving it a name now. So it shouldn't be too bad. Now, of course, if it is bad, as always, please reach out to me. I want to talk about a few more things about tornadoes before I let you loose, though. So there's a difference between every different type of tornado. No two tornadoes are created equal. Some tornadoes are capable of ripping shingles off of your roof. Other tornadoes are capable of ripping your entire roof off. And other tornadoes are capable of just destroying your entire house. Well, in order to be able to categorize each of these individual types of tornadoes, a scale was created in the late 1960s called the Fujita scale. And this scale actually reigned as sort of the big scale that everybody used around the world for classifying tornado intensity until 2007. Obviously, between the late 1960s and the late 2000s, technology changed quite a bit, and our understanding of tornadoes changed quite a bit. And so, rather than throwing out the scale and doing something completely new, we only really saw the needs to just tweak it. Basically, we took the football and ran with it. And so we came up with what is called the Enhanced Fujita Scale. And the way that the Enhanced Fujita Scale works is tornadoes are rated based on the damage they cause. So if you're taking my online class, my online lecture class, I have pictures showing like the different types of EF tornadoes and what they cause, how the damage it causes. But I'll just give you the 30-second flyover here. An EF0 tornado, very little damage. An EF5 tornado, total destruction. The last thing I'll talk about with this particular exercise has to do with being able to identify tornadoes and then determining their path. So first let's talk about the path. So this is actually a map from this exercise, from this investigation, and it shows the path and width of a tornado that you're going to be looking at in a town called Salina. And basically what's happening here is this red area represents the length of the tornado's path. But you notice, though, and I'll also mention that the tornado started here, right near Salina, and then it traveled in this particular direction. Not going to tell you what direction it is, but just remember, north is on the top, south is on the bottom, east is on the right, west is on the left. So that should give you your answer. But notice that as the tornado was progressing, this blob became wider. Well, that just indicates that as the tornado was traveling, its funnel also became wider. So that's really all that you need to know about that. The last thing I'll talk about is identifying tornadoes on radar. And so this is actually that same Salina tornado. And the way that this works is, if you remember from several modules ago, we actually talked about radar images. And there are two types of radar images here. This one up here is called the reflectivity. This one down here is called the velocity. The reflectivity identifies heaviest rainfall. And if you notice, the heaviest rainfall, the darkest reds, are just to the east and northeast of Salina. And then down here, the velocity, if you remember, velocity is basically based on, is the wind blowing away from the radar site or towards the radar site? And just to help out, I actually put a star up here indicating where the radar site is. And what I recommend doing is, in determining what direction this tornado is moving in, what I would do, and I'll actually grab, let me pick I'll pick yellow. In order to determine what direction the tornado is spinning in, is it spinning clockwise or counterclockwise, what you need to do is, this green area here represents winds that are blowing towards the radar. So what I would do is draw an arrow through the green that is pointing towards the star up there that represents where the radar is. Then on the other side here where you see these reds, that represents a region where the winds are blowing away from the tornado, or sorry, away from the radar. So what you want to do over there is draw an arrow pointing away from the radar. And so what you see is, you see this motion where over here the winds are heading up and to the left, down here they're moving down and to the right. If I were to have some kind of marker in between these two, and you can even do that, go grab a pen right now or something and actually put it in between your two hands. Your upper hand, move it up and to the left. Your lower hand, move it down and to the right. And you'll see a circulation that looks kind of like that. Now, I won't say exactly what it is. I want you to determine what it is. But there you go. And that's really it for this particular investigation. As always, questions, comments, concerns, please don't hesitate to reach out to me. There is a little bit of calculations that you have to do, but it's nothing too difficult. And I actually give some hints in the answer sheet. And that's the other thing. There are a few difficult questions, and I try to throw hints in there. So that's all for now. I'll see you for the next investigation, which is on something that a lot of people consider to be similar to tornadoes, but they're actually very different: hurricanes. So I will see you then.